today practical is related with the, it is totally related with the finding out the electrical conductivity, right? So conductivity or electrical conductivity, you all know, when there are, when an electron, if we find, if we define electricity, what is electricity? It is the, transfer of one electron from, one electron from one point to the other point, right? So that we call as the electricity, or flow of electrons is called as the electricity. But again, when we say that the flow of electrons is called as the electricity, the flow of electrons take place through only, some of the materials, and other, for some of the other materials, the flow of the electrons won't be taking place, right? So we say that it is, no, normally we say that a good conductor will no, help for passing of the electrons. So it is, we call it as a good conductor of electricity. And nextly we have bad conductor of electricity as well, in which we do not, no, the electrons do not take place. We do have semiconductors, but that is not the, no, that is not that, it is not the topic that we are going to focus upon. So this is just an introduction that we have good conductor of electricity and bad conductor of electricity. Now we all know that the water is a good conductor of electricity, right? So water, the electrical current can be passed from one point to the another point, and water is one of the best good conductor of electricity. And why the water is good conductor of electricity? It is not because of the presence of hydrogen and hydrogen atoms in water atom. It is because of the, the salts that are present into the water, right? So particularly because of that salts, the transfer of the electron takes place very easily, right? So now if I have to find out the, conductivity, I'll be dealing with, I'll be dealing with the conductivity happens because there are salt concentrations. So the very first line here tells us that irrigation water, which may be, no, which can be any river water, lake water, or well water, or treated wastewater, is evaluated by its total salts concentration, right? So excessive salts in the water reduce the osmotic activity of plants and diminish the absorption nutrients from soil, affecting the plant growth and crop yield. So this is very important. If there is a very huge, concentration of the salt, what will happen? The osmotic activity of the plants will get disturbed or will get reduced. Now, what is this osmotic activity? Just a second. Okay, I'll be stopping sharing this document and I'll be opening so that you also can read this. Yeah, I'm hoping that the screen is visible now. Now, the very firstly, the irrigation water, which may be, river water, lake water, or a well water, or even it can be a treated wastewater, right? So domestic wastewater will be treated in the STP, and the treated wastewater can be used for the agricultural purpose also. This all contains the, particularly the salt concentration. Now, the excessive salt concentration is not good, right, for the irrigation purpose. Now what we are going to talk, everything in this experiment will be with respect to irrigation, and why this will be with respect to irrigation, I'll be explaining it in the, due course of this explanation, right? So excessive salts in the water reduce the osmotic activity. So we were talking about the osmotic activity. And what is osmotic activity? Osmotic activity is the absorption of the nutrients, or the transfer of nutrients within the entire plant, right? So particularly if there is a nutrient that is getting absorbed from the soil, what will happen? That nutrient will reach every part of that particular plant because of the osmotic activity. So we also have osmotic pressure, right? So osmotic pressure is also, no, it is related to that particular terminology only, right? So because of the osmotic activity, what will happen? The plant transfer the nutrients and all what they need from one point to the another point, and that particular osmotic activity will get reduced. If this osmotic activity is only getting reduced, what will happen? That entire plant will die, right? And also, particularly this, irrigation, if there is a high amount of salt, the diminishing of the absorption of the nutrients from soil will also happen, and eventually what will happen, the plant growth and the crop yield will get affected. Now that affect in the sense it will have a negative impact, it will die or it won't be giving us the targeted yield, right? Now, as salt solutions conduct electricity, the concentration of the salts in the irrigation water is evaluated by determining the electrical conductivity. Now, why this is happening, that the irrigation water is affecting the plant growth and crop yield? It is because of the excessive salt in the water. And how we can particularly find out excessive salt? And now here the excessive salts are, those are correlated with the conduction of the electricity. So if there will be excessive salts, what will happen? More number of electricity will be conducted into that particular irrigation water. If there is less amount of salt, what will happen? The less electricity will be conducted through that particular water. And we'll have to remember that this salts are total dissolved solids, right? So salts come into the category of dissolved solids. They are not visible, or they're not in the suspension, right? They are always in the dissolved state. So particularly what we are going to do is, now we are going to correlate the total dissolved solids with the conduction of the electricity. Indirectly what we are going to do is, indirectly we are going to correlate the salt concentration with the conduction of the electricity. So we may have a sample, and we are going to find out what is the electrical conductivity of that particular sample, and depending upon what is the electrical conductivity, we are going to decide whether that particular water is suitable as a irrigation water or not. See, not all water is suitable for the irrigation purpose. For example, I can give you an example of the saline water. The water that we take from the water which is available in the sea or the oceans is not good for not good as an irrigation water. And if we ask why, any small child, even a small child will be telling that it has a very huge concentration of salts. But now here, how to measure or how to see whether that particular salts are present or not, and if present, what is the concentration of that particular salt, right? So particularly TDS can be because of many things. Total dissolved solids can be out because of many things, right? But if you have to find out specifically the salt concentration, we can find out, and that particular can be related with the irrigation water. And if that particular irrigation water is to be used or not, that solely depends upon the concentration of the salt. Now, how we can define the electrical conductivity? Electrical conductivity is the reciprocal of electrical resistivity. So you already have seen what is the electrical resistance, right? It is the resistance to the passage of the current, right? And particularly we that resistance is measured in the ohms, right? Ohms of a conductor, right? And now particularly what is the definition of electrical conductivity? Electrical conductivity is the reciprocal of the electrical resistivity, which is the resistance in ohms of a conductor, which is of 1 centimeter square in cross section area and 1 centimeter in length, right? So now we are going to measure the electrical resistance via a conductor which is having a cross section of 1 centimeter square and length of 1 centimeter. So if you have to find out what is the volume comes out to be 1 centimeter cube, right? So now therefore conductivity or electrical conductance of a liquid is the reciprocal of the electrical resistance offered by 1 centimeter cube of the liquid at a specified temperature. So this is how the interpretation goes. So conductivity or electrical conductance of a liquid is the reciprocal of the resistance offered by 1 cubic meter of 1 centimeter cube of a liquid at a specified temperature. So it is expressed as moles per centimeter, right? So moles, that is the reciprocal of ohm, and normally 1 centimeter square, that particular area is kept as a constant, and this particularly remains constant. 1 centimeter length is kept constant, and 1 centimeter, this area particularly can vary, but for according to our definition, it is 1 centimeter square. So hence the unit will be centimeter is there only, so it is centimeter here. And ohm, the unit of resistance, resistance is ohm, but the unit of conductance is mos, right? So here it is mos per centimeter, or you can even write it as millimos per centimeter or micromos per centimeter, right? So this is very important. Now, normally we take a sample of like for the measuring of the electrical conductance, we require a sample of like say 50 or 100 ml, right? So 50 to 100 ml sample we take it in the beaker, but the effective the effective volume of the sample that will be used for measuring the electrical conductivity is only 1 centimeter cube. Okay, so here also you can no, here you can understand. So how many meter cube? Sorry, 1 centimeter cube. So how many centimeter cube of liquid is required for measuring the electrical conductivity? Is only 1 centimeter cube, right? And that is enough for measuring the electrical conductivity. But we normally take a 100 ml. Normally we say we take a sample between 50 to 300, 50 to 100 ml, because we want to dip that particular electrode properly. And but the effective use of the sample for giving us the electrical conductivity value is only 1 centimeter cube, right? So now low salinity. So if the electrical conductivity is less than 300 micromoles per centimeter in irrigation water, no, particularly it is to said as to be it is having low salinity, and the salinity generally is caused by the Ca2 plus, Mg2 plus, and HCO3 minus ions, right? So this particularly is the understanding what we have. So if we have the electrical conductivity whose value is less than 300 micromoles per centimeter, we can say that the salinity is low, and the ions present are Ca2 plus, Mg2 plus, HCO3 minus. So for example, that particular so the salinity in that particular sample may be because of the calcium chloride, maybe because of the calcium sulfate, or maybe because of the magnesium carbonate, magnesium sulfate, or it can be because of the carbonate ions, right? Similarly, if my if my electrical conductivity is between 3000 to 1000 3000 to 10,000 micromoles per centimeter, why that particular sample is said to be a high saline sample, or it is said to have a high salinity. And here, apart from no Ca2 plus, Mg2 plus, and bicarbonate ions, this no salinity is because of Na plus, K plus cations, and also because of SO4 and Cl minus ions. So it can be because of the can be because of NaCl, or it can be because of the KCl. It can be because of the magnesium sulfate, or it can be because of the calcium chloride. So here, particularly, we were here there were very less what we can say salts that were available, but here the number of salts availability will increase, and no, because of that the salinity will also increase, and the electrical conductivity value will also increase, right? There is again, if I'm having the electrical conductivity more than 10,000 micromoles per centimeter, I say it is a very high saline water, and maybe it no the salinity is caused by Na plus, seldom K plus, and Cl minus ions. Bicarbonate ions in combination with the above cations can push the pH up to 8.3, but when carbonate ions are present, pH may go up to 9, making water unsuitable for irrigation, right? So this is very important, right? So you should understand why why this is happening. So no, high saline water may be may have a very huge pH. The pH of like say 8.3 and 9 is not suitable for the agricultural purpose or irrigation purpose. Normally the water that we drink is in the range, the pH range is in pH range is 6.5 to 7.5, and the same water we consider suitable for our irrigation purpose as well. But if you say that the pH is more than it is 8.3 or more than 9, so what is that water? It happens to be a basic water, and basic water will create it will be definitely creating some adverse impact on the on the irrigation purpose, or even if we drink that particular type of water which is a basic water, that will hamper our growth as well, or it may lead to some different diseases only. So electrical conductivity is proportional to the ionizable fraction of the dissolved solid concentration. Therefore, the measurement of the conductivity may be used to obtain a quick measurable of dissolved salts in the water. Now, what is this particular line? This particular line tells us that the electrical conductivity can be used to find out what is the concentration of the dissolved solids in the water. Because why electrical conductivity is there? Because some of the salts are there in the some of the solids are there in the dissolved state, and because of those dissolved solids, or we can say dissolved salts, the electrical conductivity is happening. So there is one empirical formula that is being derived, which tells us that if we have electrical conductivity value and some few more values, we can find out what is the concentration of the dissolved salts. Now this is the famous question, or you'd say the most repeatedly asked question for this particular for this particular experiment. They will be asking you, see, I will be giving you a electrical conductivity value. How can in what different way, or how this particular value can be used to find out some different value? So we get confused, right? So electrical conductivity is given, and how electrical conductivity value can be used for doing some other thing. We say that the electrical conductivity value will be helpful for us to decide the salinity or the crop that we can take, but we forget that the electrical conductivity value can be used for finding out the total dissolved solids concentration as well. So here we have a formula which can be used for the water, which is in the range of pH to 9, and in the temperature range, which is 10 degrees Celsius to 40 degrees Celsius, which is the range of the temperature that is available in most of the part of the world. So I can find out what is the total dissolved, that is inorganic solids, total dissolved inorganic solids, by using this particular formula, where it is equal to K into 1.02 raised to T minus 25 into the electrical conductivity value. The value that we get for the the value that we are going to consider for this conductivity should be in the unit of micromoles per centimeter, right? So this is very, very important, and it should be understood that the electrical conductivity value can be used for finding out the TDS and vice versa, right? So here there are particularly different different units, or what you can say, different symbols that they have used. So the K stand for, this K is a factor depending upon the electrolytic character of the water, and the value particularly different water, it will be different. So K is equal to 0.7 if dissolved salts in the irrigation water contains 83% of the salts which conduct current. K is equal to 0.58 if only the electrolyte component of the irrigant is required. So now particularly you can take different values of K depending upon what is the nature of the electrolytic character of the water. There is a table, standard table, that is available regarding this. So you can select a K value, right? And T is the temperature here, and conductivity is in the micromoles per centimeter. So you'll be getting the value of the inorganic total dissolved solids in the with a unit of mg per liter by using this formula, right? So now let's particularly correlate a soil with the conductivity value, right? So light textured soil having clay content of less than 10% have excellent internal and surface drainage. EC of irrigation water from 6,000 to 8,000 moles per centimeter may be considered safe for semi-to tolerant crops because of the effective leaching action. So if I'm having a light textured soil which has a clay content less than 10%, so which irrigation water I should use? I should use the irrigation water of having the concentration or having the electrical conductivity value in the range of 6,000 to 8,000 moles per centimeter. If I'm having a medium texture soil in which the clay unit is, clay has a percentage of 10 to 20%. So in that particular case, I can use the irrigation water which has the electrical conductivity in the range of 4,000 to 6,000 moles per centimeter, right? Similarly, for the heavy egg textured soil with a clay content of 20 to 30%, these has the moderate drainage moderate drainage application, and the electrical conductivity in for such type of soils can range is suitable to be in the range of 2,000 to 4,000 moles per centimeter, right? So deep black soil. So if I'm having a deep black soil of clay having a clay content more than 80%, what I'll have to do? I'll have to use an irrigation water whose electrical conductivity is between it is 2,000 moles per centimeter. That is the maximum limit that we have, and that particular maximum limit will be 2000 moles per centimeter for this particular purpose, right? So I'm hoping that you have understood this. No, hope that you have understood this, because what we are going to do here is that no, what we have done here is we have correlated the soil with the electrical safe electrical conductivity value. So if the if you see, if the clay content is less, higher irrigation, the irrigation water having higher electrical conductivity is, it is good. So if the as the clay content is increasing, the electrical conductivity ranges are also, the values are also going to get decreased, right? So this you should understand. So salt tolerance level for some crops are determined by maximum EC values, beyond which normal crop yield starts dropping, right? So we have salt tolerance level for some of the crops as well. For example, if I'm having a field crop like corn, so the if I take a sample, normally the electrical conductivity of the standard soil sure no is in the 1700 micromoles per centimeter, and the irrigation water that I need to use is 1100 micromoles per centimeter. So this is only for specifically for the crop for corn for good yield, right? So the even we can find out the electrical conductivity of the soil. So if I have to take a corn crop in a particular soil, so the electrical conductivity of that particular soil should be 1700 or so, and the electrical conductivity of that irrigation water that I am going to use should be 1100 micromole per centimeter, right? Similarly for the wheat, the values are given here, 6000 and for soil and 4000 for the irrigation water. For cotton you can see the irrigation, the standard soil extract which can have particularly that's 7700, and the uh, irrigation water electrical conductivity is 500. So I'm not going to discuss all this particular thing, but I just want to make you aware that this electrical conductivity value has a huge application in the irrigation water, because we have to use this treated wastewater some at some place or another, and if it is to be used as an irrigation, right? So for irrigation, there should be there are some standards that we need to that we need to consider, and there what we have is the uh, and that at that particular juncture, these standards are very very important. So classification of the electrical conductivity of irrigation water in relation to its application, right? So this was particularly this is related with the application. So if I'm having the electrical conductivity of that irrigation water at 25 degrees Celsius, and the unit is micromoles per centimeter. If it is less than 250, we say that the irrigation water is low, and this particular water is suitable for all crops, field crops, no forage crops, for example, various types of grasses, vegetable crops, and the fruit crops on the soil. So, the irrigation water whose electrical conductivity at 25 degrees Celsius is less than 250 is considered as best suitable for all the crops. So irrespective of which crop you are going to take, this is the best what you can say water for usage of the irrigation purpose. So nextly we have no electrical conductivity at no the range of irrigation water in the range of 250 to 750. So the salinity is said to be a medium salinity, and it is suitable for the field crops, forage crops, vegetable crops on the soil with moderate drainage. So you can see here it is not suitable for the fruit crops, right? And suitable for field crops, forage crops, vegetable crops on soil with moderate drainage. So you'll also this is okay that it is electrical conductivity of the irrigation water is this. But again, we'll have to, if this particular type of water is to be used for such type of application, so what we'll have to think of now, we'll also have to think about the soil, if that particular soil is having a moderated drainage or not, right? Similarly, if I'm having no, if I'm having the irrigation water whose electrical conductivity in this particular range, so it is said to be highly saline, and it is suitable for some salt tolerant field crops. For example, cotton, wheat, some varieties of the grasses, and some variety of the fruit crops as well. So, for example, pomegranate, date palm, or no, or these are the examples. So electrical conductivity plays very important role in deciding the crops, as well as the we can decide a crop depending upon what is the electrical conductivity of the irrigation water that is available, and what is the type of the soil that is available in our type of the soil that is available in our farm, right? And on that we can decide. So even for the electrical conductivity value in the range of 20 to 2250 to 2000 to 3000, it is very high saline soil, and it is suitable for very few salt tolerant crops, for example cotton and wheat, and it is suitable for very few varieties of the grasses only. So electrical conductivity of your saline water will be very high, and hence it is not suitable for any type of crop. You don't grow any type of crop in your saline water, right? So in addition to the affecting plant growth, salinity in water also affects the fish culture. So apart from the apart from the irrigation, I can also use this treated wastewater for no for fish culture, right? And no in if that particular salinity is more or less, that is also going to affect the fish culture business that I'm doing. Salinity reduces solubility of oxygen and results in diminished intake of oxygen through all the gills of fish. Now, I don't need to highlight this particular point. We have already seen in our DO experimentation that as the value of salt concentration goes on increasing, the dissolved oxygen content goes on decreasing. So here, no, we have already seen that the salt concentration is inversely proportional to the value of DO. So more is the salt concentration, lesser will be the DO. So what will happen if I'm doing, or if I'm going to plan some uh, doing some fish culture in that particular sense? So I'll have to take a decision whether to go for that or not, right? So nextly we have some of the standards that are recommended. These are the standards, right? Up till now, what we have seen, these ranges on these, all are developed with the help of the some experimentation and the experiences, right? Even the standards are developed with the help of some experience and experiments, but the standards related with the electrical conductivity are this one, right? So tolerance limits for inland surface water for irrigation. So if I have to use this, if the water is to be used as a irrigation water, the electrical conductance at 25 degrees Celsius, the maximum value is 3000 micromoles per centimeter. If this is the criteria that the if the electrical conductance value is less than 3000 micromoles per centimeter, then I can use that water for the irrigation purpose. Even particularly if I have to think of the TDS concentration, that is the inorganic TDS concentration, we have already seen in the TDS experimentation as well. So the concentration, the maximum concentration of the TDS is 2100 mg per liter. So you can adopt, you can calculate it from the help of the empirical formula that we have. And if it is exceeding 2100 mg per liter, we can't use it for the irrigation. If it is less than 2100 mg per liter, it can be used for the irrigation purpose. Similarly, if I have to go for the fish culture, the electrical conductance at 25 degrees Celsius max should be particularly less than 1000 micromoles per centimeter, right? So the maximum permissible value for a water to be used as a fish culture is 1000 micromoles per centimeter. Now let's see the application part. No, sorry, the principal part, and no, the procedure part I won't be explaining because it is a simple experiment. I will be performing it, and then you can see the video. It is very easy to understand. So principle is determination of the conductivity is based on the measuring of the resistance of a solution of a area, no, of a column of solution of area a centimeter square length and 1 centimeter. So we have already decided that this that the value of a that we are going to use is 1 centimeter square. So the specific conductance is given as 1 by a into 1 by r, So A value is here 1, so 1 by 1 is 1, and hence we get the value of conductance as 1 upon resistance. So where R is the resistance offered by the solution, and 1 by A denotes the cell constant. In our case, it is equal to 1. So what we do require here, we require a conductivity meter, which is going to tell us the reading. We require 1000 ml beakers, 1000 ml measuring 100 ml beakers, 100 ml measuring cylinders, and the blotting paper, right? So we require only this, either of these two chemicals that will be requiring. So either it will be 0.1 normal case KCl, that is potassium dichromate, or either it will be a standard salt solution, that is a KCl. So procedure is very simple. We'll be taking the sample in this particular type of beaker, which is of 100 ml. We'll be using this machine, and what we are going to do, we are going to dip the electrode, and here on this display we'll be directly getting the electrical conductivity, right? So all the how this machine will work, this machine will going to actually measure the resistance, and with the help of the software, what it is going to do, it is going to convert the resistance into the conductance, and it is directly going to give us the value of electrical conductivity on this particular display. So you can even change with this knobs that are available. You can change the unit as well, so that you can switch from moles per centimeter to micromoles per centimeter or millimoles per centimeter. That can happen. So this is a small pH. No, you have already seen pH measurement device. So it is just like that, right? So when I'll be explaining it, is no, it will be helpful for you. So this is the reference chart, how that is to be used. We have already seen how the sampling is to be done, right? So here observation table, we'll be having different type of sample. We are going to note down the temperature, and we are going to note down the conductivity. We'll be adding one more table here, remark table, and no, then we can decide whether it is a high saline, low saline, or moderate saline water. So this is how this will work, and no, we'll be seeing the video of it, and I will be telling you when the video gets uploaded.
Okay, so we are going to start with the electrical conductivity experiment. We have already seen the theory part of electrical conductivity experiment. Now we are going to see the practical performance of it. So this is the electrical conductivity meter that we are going to use for this entire practical. Right, so practical is very simple. This is electrical conductivity meter, and this is the electrical conductivity electrode that we are having, and this electrode is going to give us the reading, and that reading we are going to note down. But before starting with the experimentation, we are going to calibrate this equipment. How the calibration is to be done, that is very important. So what we have, the current temperature, the instrument is to be calibrated along with the temperature. So the temperature that we have is 29 degrees Celsius, and for 29 degrees Celsius, in the table that they have given, that the machine should show 13.87 reading. So now the chemical that we are going to use for the standardization purpose is the 0.1 normal potassium chloride, that is 0.1 normal KCl. So that I will be dipping, and when I will be dipping this, the machine should show me the reading as 13.87. If it is not so, what we are going to do is we are going to adjust it. So we are going to wait till this reading becomes stable. Now, as of now, it is showing me 13.88, 13.9291. It is approximately equal, but if it would be different, what would have been done? This is the screw that they have given us, and then we are going to keep this, and we are going to turn this knob or turn this screw. So you can see the readings are changing, right? So if I move in the clockwise direction, the readings are changing, they are increasing, and if I am moving in anti-clockwise direction, the readings are reducing. So I will be adjusting it now to 13.87. It is a very sensitive calibration, so even the nearer value will be doing. So not exactly 13.87, if it is 13.88 will also be okay. Yeah, so it is 13.89 as of now it is showing. So I won't be disturbing it because it is very sensitive. So approximately same value we have got. So this is how the calibration is done. Now what we are going to do is we are going to plot a calibration curve for determination of the salt content. So these are the various concentrations of KCl that we have selected, starting from 300 mg per liter to 3000 mg per liter. So we are going to do that to find out the salt concentration against the electrical conductivity value. So we are also, we are serving a dual purpose. We are finding electrical conductivity as well as what is the salt concentration, right? So what I will be doing is I will be showing you like one or two readings firstly, not all, because it may take some time, but I will be giving you the readings for all this, right? So firstly, let's start with 300 mg per liter, and let's find out what is the electrical conductivity for it. So when you take out the electrode and dip it in the another sample, the electrode should be washed, right? So this is the distilled water that we have, and we are going to wash the electrode with this kind of setup, right? So after washing this electrode, what we are going to do is we are going to take 300 mg per liter of concentration sample, and we are going to find its electrical conductivity, right? So after calibration, this is our first thing that we are going to do, right? So the reading that is coming out is 1.1, and we are going to record this reading for our further calculation. We are going to wait for the reading to be stabilized. Yeah, so it is coming out to be 1. Okay, it is changing. Okay, it is stable. It is 1.29. Okay, it is, yeah. Okay, 1.28 is the reading that we are going to give, right? The solution I am again going to put in the volumetric flask. Right? So we are going to find out the electrical conductivity for another concentration, which is 600 mg per liter, and likewise we are going to do it till 3000 mg per liter. So again we will have to wash it. And then the electrode will be dipped into this as well. So the reading that is coming is, let's allow the stabilization of this reading. Okay, it is fluctuating between 1.75 and 1.76. Now it has got stabilized at 1.76, and this reading will be noted. So what we are going to do is we are going to find out this concentrations of or electrical conductivity of all these different concentration, and that will be helping us for the finding out the calibration curve, and from the calibration curve we can find out the concentration. Now what I am going to do is, this is the wastewater sample that we have. It is the inlet of your STP, and we are going to find out the electrical conductivity value. The calibration will be readings for the calibration curve will be taken afterwards. I've shown you two demo readings, and I will be showing you what is the reading for the wastewater, what is the electrical conductivity of the inlet of the STP plant. So I'm going to wash this. Washed. We can directly keep this and stir it for, and the solids are important. We are going to dip the electrode, right? So the reading that we are going to get is, it is 0.67, right? So this is the electrical conductivity of the wastewater that we have got, and particularly the salt concentration for this wastewater sample is also to be found out with the help of the calibration curve. So that I will be explaining you in the calculation video.
This is the calibration curve that I was talking about. So what we have done is we have taken the readings for 300 and 600 mg per liter. But in your term work part, I have given you all the readings till 3000 mg per liter. So we have the reading from 3000 to 300 to 3000 mg per liter of concentrations, and the corresponding electrical conductivity values are also known. So what we can do is for every concentration, the corresponding electrical conductivity value can be plotted. So you'll be getting such dots across the graph, right? And all those things, all these graphs, all these points on the graphs are to be properly joined. So the line will be passing through no, the origin, that is 0 0, and it will be making a 45-degree angle as well with the x and y axis, right? So now we have got the electrical conductivity values for the wastewater samples or the samples under the consideration. So what we can do is we can consider, we can pull out a point of that electrical conductivity on y-axis, and corresponding value of salt concentration from x-axis can be found out. So in that way, we'll be getting an electrical conductivity value. We'll be also getting the salt concentration. Depending upon the salt concentration that we have got, the reference tables in the manual can be used for classifying that wastewater as of what salinity it is having, and then we can also with the other reference table can judge which of the crop can be taken by using that wastewater, or which crop is suitable for that particular wastewater. So that can be written in the form of the conclusions.